Sir,
Yeah,
sir, when is the end semester exam?
Tuesday, no? Next Tuesday.
Yeah, but uh, I don't know. In topology class, the sir also said that apparently they're not following the timetable now. It seems so.
If you want to change, we can change. Rajeshwari told me I mean, she sent a timetable where it's mentioned Tuesday. So it looked
Yeah, and then
okay with you. So now
they
if
also sent another mail next time, said that you can ignore
shall
this
we
mail,
discuss
something
this
like that.
after the,
So,
shall we discuss this after the class? Okay.
yes, sir. Okay,
I'm getting
okay,
ready. So we'll discuss it after.
yes, sir. Yeah, yeah.
Okay. So this trace was defined in, I mean, in one of the presentations, the trace was defined, but it was assumed to be a compact operator and slightly, it's after the Hilbert-Smith definition, the trace came. So I didn't really like that. So I will prove few things which are, I mean, then you can look at the presentation for some. I am not going to do everything, whatever is done in 2-3 presentations. I will do some basic. Then you can some of them. I mean, the dual of trace class operator is BFH. All those things you can look at it later. Okay. So okay. I mean, the dual of compact operator is trace class. Dual of trace class is BFH. That was proved by Vritabhuta. So so those things I will not do. So and that proof was clear almost. So uh, if you look at the video, it will be clear. Okay, so I will only do some of the. I mean, basically the definition. I am not very happy about the definition of the trace class. So trace class has to be defined like this. So let T be in B of H. Let T be B of H and T greater than 0. T is a positive operator. T is a positive operator. Okay, then fix. Initially, we will fix an orthonormal basis and define the trace, and then we will prove that it is independent of orthonormal basis. Okay, fix an orthonormal basis En, and I mean t greater than t positive means the inner product txx is greater than or equal to 0. So that's what our definition is, and which is equivalent to saying t is equal to some s star s for some operator s, and we add some property. It has a square root and all those things. It has a unique positive square root and all those things we have already proved. Okay, so we will I mean here we will use the definition that t of txx is greater than or equal to 0. So for any fixed and orthonormal basis, so now the definition depends on this orthonormal basis for the time being. So define trace of t equals summation t summation t en. Okay. So this is the definition, and this makes sense. And this is a number in 0 to infinity. It can take the value infinity also. This is like defining an integral. Okay, so you can define it for any integral. You can define for any positive measurable function. Similarly, for any measurable function is replaced here by an operator, and by taking this orthonormal basis, you can define this for any positive operator. You can define this. This is well defined. So this, but it may take the value infinity. That means the trace is infinity. That's all. But infinity is well defined. I mean, it's not like infinity minus infinity will not occur here. But we cannot do this for a general operator. So for that, we need some. Similar to what we have done in measure theory class. If for a general measurable function, we have to have the integrability condition. So that's what we will have here also. So we define trace like this. Then first we prove the following. We prove that. So the first proposition for all t in P of h positive. Okay, trace t star t equals trace of no, this is for any operator. I mean, because t star t is positive, so that's well defined. So trace of t star t equal to t t star. Okay. So this we want to do. So proof. So trace of t star t, let us just evaluate it and we'll get it. I mean, this is with respect to assume that there is a fixed orthonormal basis behind the scene. Okay, we are going to evaluate this trace with respect to that. So we haven't proved yet that it does not depend on the orthonormal basis. So with respect to the trace, with respect to orthonormal basis. So trace t star t equal to summation. So m over n t e n. Sorry, t star t e n, which is equal to summation n t e n t e n. So these are all positive. I mean, this is t star t and t star t is positive. So this is a positive and this is also positive. T e n t e n. You can take the star that side. Now you can evaluate this t e n with respect to the orthonormal basis. So that is summation n, and you can bring the summation outside because inner product is continuous, of course. So this is equal to summation t e n e m e m. You can expand this t e n with respect to this orthonormal basis e n. Okay, so I'm using a different index e n. So times t. So you can write like this. Okay. So this is equal to summation n, summation n. You can bring that outside also. T e n e m and e m t e n. Notice that this is positive. I mean, this is its conjugate. The first term, the conjugate of the first term is the next term. I mean, the conjugate of t e n e m is e m t e n. Okay, so this is just mod t e n e m square. So which is positive. So since these terms are positive, we can interchange the summation. Notice that this is greater than 0. So interchanging the summation, we can interchange the summation because that's positive. So which is same as I interchange the summation and take it inside. Okay. What did I do? So this is just em. Okay. And then t e n e m, I'm taking it inside in the, I mean, the second inner product, the second, I mean, it's the where it is conjugate linear. I'm just taking it inside, so the inner product will get flipped. So this is equal to em t e n. So t e n. Okay, and I've just taken it inside as a conjugate. Okay, so and I have interchanged the summation also. So this is em. So now I can bring that t e n here. So this is just t star em. Okay. And then this is t star em, en, en. Okay. Now this is just, we take the summation n inside, and that is just t star em, you expanded in en. Okay. So this is just summation over m, t star em. This is just t star, this is em, sorry. This is em. Okay. I mean, t star em as well. So this is just t star em, you have expanded it in the orthonormal basis en. So this is just t star en. So now this is just trace of, I mean, you can bring the t star this side, which is t star, and which I'm just swallowing one step. This is trace of t star. So hence, okay. They just expanded it and then interchanged the sum and did something, and it's very trivial. Okay. So this is, so our trace, which whatever we defined in terms of a fixed orthonormal basis, satisfies this. So as a corollary to this, trace of, or let u be unitary, u in B of h, unitary, it's a unitary operator, then trace of ut u star equal to trace of t for all t greater than. So notice that ut u star is positive. I mean, for any operator, if you have any operator v, I mean, it need not be unitary, any operator v and t is positive, then this is positive. Because this you can write it as v t power half times v t power half star. Okay? And something SS, it's in the form of SS star, and anything written in this form is positive. Okay? So because of this, that is positive. So ut u star is positive. I mean, in general, this is, I mean, I said that if t is any operator, any positive operator, t is positive operator, then Vt V star is positive for all V. Okay. But in general, if you have a unitary operator, it will preserve any, I mean, this T going to UT U star is an actual isomorphism. It will preserve all properties. I mean, if you have an isometry, it will be an isometry. If you have a projection, it will be a projection. So this T going to UT U star is an isomorphism. So it will preserve all the property, in particular positivity also. But positivity is preserved by a much, bigger property. So any V will preserve the positivity. Anyway, so the trace is well defined for UT U star, and that is equal to trace T. Okay, so this will imply that the trace does not depend on any orthonormal. This will come to this. So we will prove this. The proof is clear because trace of UT U star equal to. So you can take this. This UT you can take it, and this is just. I will take. Sorry, this is equal to T power half. What should I do? I think this will work. This is T is positive, so you can write it like this. Okay. So now this is, you call it as, this is one operator, this is another operator. Okay, and we have proved that trace of T star T is same as TT star. So we can bring it here. U star. What is it? So no, T star. I have to take the star of that. So that is just T power. Sorry, U star of that is U T power half. I just have to bring it. No, this is in the form of T star. I don't have to take the star. This is just, I can just take it the other side. That's all. This is same as 3 T power half U star U T power half. Right? This is what this is in the form of T star, and I will just written T star T. Okay. So this is equal to trace of U star U is 1. So T power half times T power half is T. So this is equal to trace T. So we have used this proposition. Trace of T star T equal to trace of T star for all T. So in particular, this is true for this operator, and we have proved that trace of UT U star is trace of T. So now corollary is trace does not depend on ONB, particular ONB. That is because if we have a different ONB, En, if trace is defined with respect to proof, suppose trace is defined with respect to En, and Fn is another orthonormal basis, ONB, then U is an operator, unitary operator from H to H, which takes En to Fn. Okay. Then trace of U T U star equal to summation of this inner product UT U star. Maybe I will take from Fn. UEN equal to this. I will take Fn to En. Or I have to take U star here. If you have two orthonormal bases, then there is a unitary which take one orthonormal basis to another orthonormal basis. You can define it that way and extend it. En. And then you can take the U star that side, and U star of En is Fn. So this is same as T Fn, right? But then this is also same as trace of T by the previous proposition. So which is equal to summation Ten. Okay, so summation Ten is same as summation Tfn Fn for all T for positive T. So it does not depend on orthonormal basis. This is okay.
So can I show the theorem also?
This theorem. Trace.
Okay.
This theorem or this? This.
No, the corollary. The corollary.
No, this corollary. Wait, the corollary is trace of UT U star equal to trace of T. Okay. Trace of UT U star is, if you expand trace of UT U star, trace of T equal to Ten En, which is equal to trace of ut u star, and trace of ut u star is ut u star. You just expand it on, I mean, just evaluate on en, you get fn, tfn, fn. U star en equal to fn. So you just evaluate it and you get this. So some trace of t with respect to one orthonormal basis is same as trace of t with respect to another orthonormal basis. I have some problem in the tongue. I mean, I had a headache. I had some tablet and my tongue is, it's not, I mean, there is a problem. Okay. So I may not pronounce correctly everything.
Yeah.
Okay. So this is proof. Okay. Okay.
Yeah. Okay, sir.
Okay. So this does not depend on any orthonormal basis. So what is next? So next I want to prove that if we take any operator, so this is next proposition. I want to prove that, I mean, in the presentation or in Sundar's book, it's assumed that trace, in the definition of trace class operator, it is assumed that trace class is, I mean, it satisfies some property and it's also compact. Okay, so that is not needed. Trace class will imply compactness. In fact, trace of any power p is smaller than infinity will prove that it is compact. I mean, usually we will say something is trace class if the mod t is, the trace of mod t is smaller. I mean, the trace is smaller. That's what you will. I mean, if a function integral, the mod of the function, I mean, if you have a function, the integral of the mod of that function is smaller than infinity. That's what we call as integrable. Okay. Similarly, if you have an operator t, you take the mod of t. If that has trace smaller than infinity, we call it trace class. Okay. I mean, I haven't defined. I will define it after this proposition. So if t is in B of h, an operator. Okay.
Sir?
Yeah.
Sir, we have defined trace class operators as a positive operator that
We have defined, we haven't defined trace class operator. For positive operator, I have defined what is trace. That's all.
Oh, yes, sir. Okay. So we are now going to define trace class.
Yeah. After this, I will define trace class. By trace class, we mean the trace should be finite. Okay. That's what trace.
Yes.
Okay. What do you say about that integral trace being finite something?
This is an analog. I mean, trace is just a non-commutative analog of integration. In fact, any linear functional is a non-commutative analog of, I mean, any state. What do you call a state in the C-star algebra theory, which was defined in the Gelfand-Neymark theorem. Gelfand-Siegel construction. State is a non-commutative analog in integration. Okay. So this is just a trace is another. See, the trace can take the value infinity also. This is a semi-finite linear functional. It can take the value infinity also, and it takes finite on some particular class of operators. Okay, so which are actually dense in the strong topology. That strong topology which we defined, it's not dense in norm topology, but it's dense in strong topology. Okay, so it's on a dense, strongly dense subspace. You can define this trace. Okay. Anyway, that's
So
it's like an integration. That's what I want to say. Trace is like a non-commutative integration. Okay. I want to ask something.
Yeah. So the place where it is finite is called trace class.
Exactly. That's what I will define it. Okay.
Okay, fine.
So now t is in B of h, and trace of mod t power p is for finite for some p greater than 0. Okay. Then what? T is compact. So proof. Okay. So it's enough to prove mod t is compact. Okay, if mod t is compact, then p is compact because of polar decomposition. So if t is compact is equivalent to mod t is compact. Reason t equal to u mod t. So if and I mean for some partial isometry u and mod t is mod t. For some part, I mean this is polar decomposition. Okay? Polar decomposition is unique. Okay? And also it is the case that mod t equal to u star t. This is true for there is a u partial isometry occurring in the polar decomposition, For that partial isometry, mod T equal to U star T. This is because that partial isometry, that has kernel perp equal to this range. That has some initial space and final space, and that's so this U star is U star. The U star is
use the projection.
Isometry.
Use the projection operator onto the range mod.
Correct. But when you write it on the mod, when you evaluate on the range of T, it's an isometry on that. Okay.
Yeah.
So U star U on the range of T is isometry. So because of that, U star T equal to mod. Okay. So because of this, and we know compact operators form an ideal. So if T is compact, then mod T is compact, and if mod T is compact, T is compact. It's because of this. Okay. So it's enough to prove mod T is compact. Now trace mod TP is smaller than infinity. So this implies trace mod T power P is smaller than infinity. So this implies this just implies summation mod T power P En summation n for En orthonormal basis. Then this is finite. So this just means this is finite. That's what we have assumed. Trace is finite. So I want to say that there exists n. There exists n such that this n equal to n equal to n to infinity. Right. This summation is less than epsilon. That's what it means by it's summable, right? So this is less than epsilon. So now you define Pn to be projection, Pn projection onto E1 up to En, which is a finite rank projection. Okay? So this is a projection onto the span of this. So it's just a finite. You are just taking finitely many vectors, so it's a finite dimensional. This is finite rank projection. Now I multiply this Pn with so now I want to. So now what happens? I hit that operator T mod T power T with 1 minus Pn on both sides. I take this norm. Notice that this was already mentioned in our one of the presentation. Notice that norm T is so. See this. Where did we prove that does not depend on orthonormal? So here. Okay. So we have proved that trace does not depend on the orthonormal basis. So you can take any vector to start with any vector x and get an orthonormal basis starting with that vector. Okay. So in particular, this Txx. This. Notice that Txx is less than or equal to trace T for positive T. Okay, for positive T, this is true for all x. So this implies norm T is less than or equal to trace T. Okay, for positive T. This was noticed in the presentation also, and Samit presentation. Okay. So because of that, this norm is less than or equal to trace of this 1 minus Pn. I have 1 minus Pn here. Mod Tp 1 minus P. Now, if you apply on the orthonormal basis En, so this 1 minus Pn will kill all. Pn is a projection onto even up to En, and 1 minus Pn will kill all vectors up to vectors even up to En. So it will start from n. So this will be exactly equal to summation n equal to n to infinity inner product Tp En, right? So this is less than epsilon. So we have got that 1 minus Pn, this whatever we have in the bracket is less than epsilon. So I want to prove that norm T power P 1 minus Pn converges to T power P. That will imply T power P is compact. And from that I want to, mod T power P is compact. From that I want to conclude mod T is mute.
So what are we trying to do here? For
I'm
by
trying
doing it.
to prove norm T is mod T is compact. That's what I'm doing. No, the proposition.
Yeah, but like why did we? Okay, fine.
Why do we
Uh,
compact operators are can be approximated? I mean, if some compact operator is norm limit of finite rank operators. Okay. So if you prove
yeah.
the operator is norm limit of finite rank operator, then it is compact. One second. So I just want to prove that it's the limit of, I mean, the operator can be approximated in norm by compact operators, by finite rank operators. That's what I'm doing. Okay. So I have taken, so I have an operator T whose trace mod T power P is smaller than infinity. So that means this, that means the whatever the summation, the tail of the summation is less than epsilon for some n. Okay. Then I have taken this projection, which is the projection onto first n or n vectors. Okay. Then I have proved that this 1 minus Pn, when you hit that norm T power P, when you hit it by the 1 minus Pn, the projection 1 minus Pn, that norm is less than epsilon. I have proved. So now I want to approximate that. What do I want to approximate? I want to prove that norm T power P minus finite rank operator Pn power. I think Pn. I can put the Pn. Maybe that was right. I want to show that this is less than epsilon. I think I need P by 2. I think that's okay. That's all. That will also work. Times square equal to. So this is by C star identity. This star times this. Okay, so which is just. I mean, this is equal to whatever I have there is mod T power P by 2 1 minus P. Okay, square. And 1 minus Pn, I can write it as, I mean, this is an operator S. Norm of any S is equal to norm of S square equal to norm of S star S. Okay, so if I write that Pn, and then P by 2 mod, this will become P, and this will become again 1 minus Pn. So I have taken, I mean, I said P, but it's actually for P by 2. Okay, this is, so this is less than epsilon. Okay. So this implies mod T power P by 2 is compact. But mod T is self-adjoint. It's a normal operator, and we have proved spectral. I mean, from the spectral theorem, this is a diagonal operator. Okay, there exists some orthonormal basis. So mod T power P by 2 will look like this summation lambda n. I think you know this notation now. En. This was the notation used for the finite rank operators, En star En. This is just the finite. I mean, this just means norm T power P by 2 of En equal to lambda n. Okay. So it acts on the orthonormal basis like this. So this implies mod T equal to lambda n power, the lambda n's are positive, 2 by P En. I mean, this all follows from spectral theorem and functional calculus. Functional calculus for compact operators is very simple. Okay, you can directly define. So from that, so I mean, and lambda n goes to 0. So this implies mod T is compact. Mod T power P by 2 is compact, so mod T is also compact. Any power is also compact. So we have proved that some trace of mod T power P is finite for some P implies T is compact. Okay. Now I want to define the trace class operator in slightly different way, and then, I mean, the reason is the following. So definition. B1H equal to span. This is just usual span, no closure, nothing. All those T greater than or equal to 0 in B of H, such that trace of T is finite. You just take the span of these things. In fact, you don't need too many spans. I mean, if you have any, I mean, it will be span of 4 operators, 4 positive operators. Any operator is span of 4 positive operators. Span of 2 self-adjoint operators, which is difference of 2 positive operators. So because of that, it's 2. Okay, B1H is this. Then I want to prove later that this is, I mean, want to prove that this is nothing but all those T in B of H such that trace of mod T is finite. That's what I want to prove. I just take the span here, then I want to prove that these two are equal. And I also define the Hilbert-Smith operator P2 equal to all those T in B of H, trace of T star T is finite. This is the same. If you evaluate it, it's the same definition. Trace of T star T En, which is norm of T En square. So summation, this is equivalent to saying summation norm of T En square is finite for all En, and it does not depend on En. All those things we already proved. Okay. So it's the same definition. So this is the Hilbert-Smith operator definition. Okay. Okay. So what is next? So now next I want to prove that whatever the B1H I have defined, that's an ideal. What's the time? So proposition. We know all compact operators. We have already shown that B1H is contained in B0H. This is all compact operator. I think this is the notation I use, B0. So B1H, whatever we have defined, that is contained in all compact operators. If trace T is finite, then that's compact. And you are just taking the span, okay, not ordinary, I mean linear span, finite linear span. So that should be in the compact, all compact operators. So we have already proved this. So this is an ideal. It's an ideal. I mean, this is not the proposition. This we have already proved. Proposition is this. Maybe I'll just say this later. B1H is a two-sided ideal. It's a two-sided star ideal. I mean, B1H is defined as trace of B1H is defined as span of all those positive operators whose trace is finite, and so it forms a vector space clearly. And clearly, trace of T1 plus T2 is trace of T1 plus trace of T2 for any positive operator, any two positive operators. And scalar multiplication is I mean, it's closed under scalar multiplication also. So it's a vector space is clear. And it's an ideal we want to prove. So how do we prove it's ideal? So we want to prove if we want to prove that if something is a span of finite linear span of positive operators whose trace is finite, then if you multiply by any operator, then that's also in the B1H. That's what we want to prove. For that we can, I mean, since the trace is linear, we can assume that the T is finite. So it's enough to prove the following. Enough to prove for T greater than 0 and trace T greater than 0 and trace T is finite and S is in B of H. We want TS is also in B1H. Okay. That's what we want. Okay. So that means it can be written as linear span of positive operators whose trace is finite. Okay. So this is a general fact, which we will be using later also. So which I will write it here. Which I will S star T for any B of Okay. This is just the polarization identity, which you can write it in for inner product. This is true for, I mean, the inner product, you are just using the conjugate linearity in one of them and linearity in the other one. So here I'm just writing it. But instead of writing st star, I'm writing s star t. It's conjugate linear in the first variable, linear in the second variable. That's all. But the same thing will work here. K equal to 0 to 3 I power k s plus I power k t star plus s plus I power k. So this, the same way which you have verified for inner product, you can verify this. Okay, the same thing. You are just using the linearity and the anti-linearity, conjugate linearity. Nothing else is needed here. So if it works for inner product, it will work here also. Okay? It's very similar to that. This is just an operator valued inner product. You can think like that. Okay? So this polarization identity is true. This is what is called polarization identity for operator or whatever. So I am just going to use this for this TS. TS or ST I want to use. I want to use it for ST. ST or TS, whatever, we will get something. The thing is, if I write, T is positive, we can write it like this. So you call one. This is one operator, that's another operator. So this is the star of that. So maybe I should have T there. TS. TS equal to T power half S. Okay. So the star comes first. So this is going to be no, S star comes. Oh, that's okay. That's okay. So I'm sorry for changing it because I'm to get the right expression. S T power half T power half. Okay. ST equal to this. So we will only prove ST. ST. So ST power half is T power half S star. Okay. So you can write it as S T power half here, but I will write it outside. Okay. Plus I power K summation here. There is a 1/4 something. Okay. That's 1/4. I power K. You will get a T power half here, but I put identity and take the T power half outside. Okay. But then there is another T power half, so it becomes T. Another T power half, I will get it from here. So which is just another S plus. So this ST power half is T power half. Yes. So I should have T. I'm sorry, changing it so many times. I'm sorry. This is just TS. Sorry, TS equal to T power half S. Then I should. What is it I want to get? I want to get this. Okay, S plus T power P. This is equal to, if I write it in that form, this is just okay. Then I will get S star here. That's okay. S star T power. So, S T power half is T power half. But then I get T power half here. I cannot bring it here. This is just, if I take the T power half here, then T power half, yes. So, yeah, so it should be, that's okay. T power half, yes. That's okay. You take one of the T power half here and put it here, but that is just T power half, yes star. I mean, you verify this. This is okay. Okay. So here also it's t power half s, and that those two t power half goes here and two. This is okay. If I use the same polarization identity, I get this. Okay, this is okay. I have written it correctly. Okay. So now these things are positive. This is equal to of the form 1 by 4. There is an I power k somewhere. This is okay, no? There is an I power k outside also. I'm sorry. Yeah, there is an I power k outside. So this is just I power k sum v star t v. Okay, where v is this. So this is summation of positive operators. So it's enough to prove that v star t v for any v, this is positive. This has finite trace. Okay, so we prove the following the claim. I mean, I have written TS in this form. Okay, so claim is if T positive and trace T is finite, okay, then V star TV trace of this is also finite for all V. Okay, okay. So that should be easy. Just because trace of V star TV, you just write it with respect to some orthonormal basis, which is just equal to V star TV En, okay, which is equal to summation T Vn Vn. Okay, that is equal to Vt. This is not less than I want to say that this is norm of V star V times. Excuse me. So I want to use another claim. So I want to prove this claim. For this claim, I do the following. V star V, V star TV as an operator, There's an operator inequality. No, something is greater than. You can compare self-adjoint operators. You can compare positive operators. This is greater than norm of V star V times T. So this is true. I want to prove. Sorry, this is this way. Another. This is less than this. Okay. So this is less than this. So for this to prove that V star TV XX, okay, is less than or equal to getting this V star. Oh, should I use that? Yes. Now, notice that I think this may work. Trace of V star TV is equal to trace of. You can apply that T power half V. You can bring it here, no? So this is T power half V, which is V star V, T power. This is using the first equality, trace of T star T equal to trace of T star. So I'm using that. Okay. Now this will work. So now this is equal to summation T star V star V T star En, which is equal to summation. T power half. T is constant. T power half. T power half. This. So this is equal to V star V T power half En, T power half En, right? Now this is less than or equal to, you can take this. I mean, V star V is, this is less than or equal to norm V star V. You can bring it outside, times T power half En. This is okay. So this is equal to norm of V star V times trace of, then you can bring the T there again. So which is equal to trace of. Okay. So because of this, if trace T is finite, then this is norm is a number. So trace V star TV is also finite. So let me go through the whole thing. So because trace T is finite, trace of V star TV is finite. So because of that, using polarization identity, the trace of TS is finite. I mean, where T has finite trace, S is any operator, then the TS can be written as linear combination of operators of this form, V star TV. And each V star TV has finite trace. So all these things imply that TS is in B1H. Is okay?
So why didn't the first first proof you tried?
Very feeble your voice.
Okay, so why didn't the first proof you tried like expanding it
Say it again.
using?
I'm not
So
hearing.
the one, okay. So the first one you tried, right? What was the problem with that?
That problem, I was not getting the right thing. No, I was not getting the V, for the V star V. I was
Okay,
getting
but
V star in
I
this
thought,
side, V star D. Then how can I write this norm V star V? I was not getting the answer. But if you are getting, you tell me.
okay, I maybe I'll check
Huh?
again. Yeah, I thought it was coming right, but maybe I'll check again. Fine.
Yeah, you can check. I didn't find it. See, I had V star V. I had V star here and V inside, and I was not able to take the norm out. Norm V star V. Maybe possible. I don't know. Here also it's possible. I don't know. This may, I mean, no, I think it was not working. It's not working. Okay. So this works.
Okay.
It's fine.
Yeah,
Okay.
fine.
Okay. So this is fine. So this says that this implies that it's a left ideal, right ideal. This is right ideal. But then it's star closed. I mean, if you take linear combination of positive operators, if you take the star, that's also linear combination of positive operator whose string is finite. So B1H is star closed. So it's left ideal means it's right ideal also. So it's a star, two-sided star ideal. Okay. So those things are clear. Okay. So now the corollary to this, B1H is nothing but, which is just I have defined it as the span of those positive trace class positive operators whose trace is finite. Okay, this is nothing but all those T in B of H such that trace of mod T is finite. So proof, this is just polar decomposition. T equal to U mod T and mod T equal to Q star T. Q star T. Okay. So if T is in B1H and B1H, then if mod T has trace finite, then U mod T will, then in particular it is in B1H. So because of that, T is in B1H. If T is in B1H, then U star T, mod T is also in B1H and it's positive. So it's clear. Okay. Because of polar decomposition, it's clear. So this is what is called trace class operators. Okay, B1H, which you can define it as all those T's in B1H, which satisfy the trace condition. Mod T is finite. This is what is called trace class operators. Okay, and B2H is what is called Hilbert-Smith operators. Okay, so now I want to prove this inclusion and then prove some identity and start. So incidentally, I remember that I haven't proved one identity for normal operator. The norm of T is equal to supremum of, so this I didn't prove it. Norm T equal to supremum of Txx. This is positive, mod of this. For any, I mean, this is clearly true for positive operators, but for all T normal, it's not clear to me, but I will give a different proof. I thought it will follow from spectral theorem. I tried few days back. I was not getting. So I will give a different proof. Yeah, I will do it on Saturday. I will give a very, we will have a very short session for 15 minutes or something. Even if you don't,
So,
I will upload it.
so maybe you can see the discussion to Saturday because that will
Wait
be.
again.
Maybe you can see the discussion to Saturday.
You want a discussion on Saturday? Okay.
Yeah.
Okay, that's fine with me because I am still, my headache is not over. So I still have.
Sir,
Yeah.
Sir, like, can you repeat the proposition you just said, like you will prove?
Now this is the proposition norm T equal to supremum of inner product Txx mod. Supremum of X in the unit ball.
This is for normal T, right?
For normal operator. This is not true for all operators. For normal operators, this is true. Which when we discussed, this is before the midterm. When we discussed the compact operators, I said I will prove this. I didn't have the proof when I was proving the spectral theorem. So I said I will prove it later. I said it will follow later. But then I didn't prove. I completely forgot. So I will do this on Saturday at the same time. It will take some 15-20 minutes. Okay. Now I am not ready with the proof. I will prove it on Saturday. Okay. You can also try using spectral theorem, and then if you have a proof, it's good. If you prove it, I will give you some marks for that. Okay. Using spectral theorem, okay, for normal operators, if you can prove it. Okay. So what do you want to prove? I want to prove this inclusion proposition. So this is finite rank operator. This is a symbol I use for finite rank operators, I think. Finite rank operators is contained in B1H. This is contained in B2H. This is contained in B0H. Okay, all of them are contained in BFH. Okay. So if T is finite rank, then I mean it's finite rank means it's compact. Mod T is compact finite rank. Okay. So there are finitely many vectors, finitely many eigenvectors for mod. I mean this is normal. Mod T is positive, so it's self-adjoint. It's normal. So there exist finitely many eigenvectors for this, and then you can obviously sum it. Okay? So this implies, I mean there exists E1 up to En eigenvectors for T, for mod T, mod T. So this implies you can sum it. It's clear mod T is B1. Okay. So any finite rank operator is trace class operator. That is clear. So and it's clear that we have already proved that for mod T power P is finite, then it is trace class. So if it is I mean if T is in B2H means mod T square is in, I mean this is what is T star T, no? T star T. So that is in trace class operator. Okay, so this is compact. So this implies T is compact. We have already proved this. Okay. For any mod T power P, the trace is finite. That means it's compact. So it just the square is finite. So square has finite trace. So it's also compact. So that also we have proved. So only thing we have to prove is any trace class operator is also a Hilbert-Smith operator. That is the only inclusion we have. So to prove B1H is contained in B2H. That's what we have. So suppose mod T, trace of mod T is finite. We have to prove that mod T square is also finite. Then trace of mod T square, I mean trace of T star T is mod T square. We want to prove it's Hilbert-Smith, so trace star T equal to mod T square. But then this is equal to mod T power half This is just clear. No? Mod T is finite. You're just multiplying by another mod T. Since Class is an ideal, this is clear. No? What is the point? What is the problem with this? This is direct, no? Hmm? Yeah. We have proved that trace class operators form an ideal. So trace of mod T is finite. So mod T square is also finite. So it's okay. That is what trace T star T is. Okay? This is clear. Okay. Oh, no. Yeah. If T is a trace class operator, that means trace of mod T is finite. Okay. So mod T square is trace T star T. That's also finite. That's clear. So there is nothing to prove. So we have proved these inclusions. So I think I have only final thing.
Sir,
Ah.
sir, about that proof, non-T equals its optimum inner product. Like, sir, about the proof, like of that proposition, like norm T is equal to supremum.
Yeah.
Sir, like I attempted that,
Yeah.
like sometime back using spectral theorem, sir. Like,
Good. You got it?
yeah, like can you please
Show it
verify,
on
like,
Saturday. Or you can show it after this now. Can you show it now or you want to show later? You can show it on Saturday. It's okay.
Saturday better because I need to go over this lecture as well.
Huh?
Saturday will be better because I need to go over this lecture as well.
Okay. So Saturday you can do it.
So just to say, so are every presentation part of the syllabus, like including the GNS operator?
No. The syllabus we will discuss after the talk. No, I don't want to discuss in the recording session.
Oh, sure.
Yeah, syllabus. I mean, so okay. Syllabus is up to trace class, Hilbert-Smith, and other things. I may ask GNS, but you can safely omit if you want. Okay? I may ask about GNS and other things. Pranam,
For the references, I found everything in Sundar's book, but this Gelfand from where did you check this Gelfand theory?
that is
that's
an spectral
from
theory book, no? Spectral theory book. There are two Sundar's book.
Oh, right. Gelfand theory, right.
Theory book, that's everything. All double commutative.
And the GNS construction, that's from where?
It's there. It's there.
Okay.
Okay. So that's all. So okay, Yusiraj, you can show on Saturday that thing. So that's good.
So lastly, when is the exam date? Because like schedule was not made clear.
What?
When is the exam?
When is the exam? Also, we will discuss after this class is over.
Oh, okay. Sorry. The
Discuss on
class is
Saturday
going.
if you want. Okay, no problem. We can discuss now. You want to go now?
No.
If you are going, we will discuss on Saturday. I mean, I have to prove one more proposition and stop. Okay, it's not a difficult proposition. And then I will stop. So B2 is a Hilbert space. Hilbert-Smith operator from a Hilbert space is clear with respect to the T star. I mean, this was already. I don't know whether it was proved in the. I don't think it's proved in the proposition, but it's clear. The completeness, I leave it as an exercise. Okay, it is clear. So B2H is a Hilbert space with respect to Ts equal to trace of T. So it has to be antilinear. So usually, I mean, the physics inner product is conjugate linear in the first variable. So people will usually write T star S, but we have to write just Ts star. So this is clearly linear in the first variable, antilinear in the second variable. And we have this trace of T star T is greater than norm of T star T. We have already proved for the trace. So because of that, it's I mean, this will be an inner product and it will be positive. Positivity is clear. And then it is strictly positive. I mean, the trace of T star T equal to 0 and plus T equal to 0 because norm of T star T will be equal to 0. So because of that, this will be a genuine inner product. And you have to prove that this is a complete. So for that, if it converges in the Hilbert-Smith norm, then you can prove that it converges in norm. So because the norm is complete and the b of x is complete with respect to norm, you will have a limit. You only have to prove that that operator is a Hilbert-Smith operator again. Okay, so I leave that as an exercise. I want to give it as an assignment, which you can submit later, or you can try this. I mean, I may ask in the exam. If I don't ask in the exam, then it's an assignment. Okay, I mean, it's okay. I will ask in the exam, or I can say, I mean, you try it. I can ask in the exam. Okay? I may ask in the exam. It's an exercise. Okay? So Hilbert space, that is clear. So what is left? Trace of ST equal to trace of TS. Final proposition. So this is what is called trace property. Okay, the trace, I mean, in the matrix algebra, for example, even in B of H also, I mean, B of H you have to be careful with finiteness. The trace is a unique operator which satisfies trace of ST equal to trace of TS. I mean, in matrix, for example, trace of TS equal to that's a unique thing. I mean, you just sum the diagonal of a matrix. It's a that is the trace is unique functional which satisfies this unique linear functional which unique positive linear functional which satisfies this property trace of TS equal to trace of ST. So that is the tracial property. This is what is called tracial property. So tracial property is more generally true. That is trace of ST equal to trace of TS for all TS in B2H. For any two Hilbert-Smith operators, this is true. There need not be trace class. Okay. Also true for T in B of H, T is B on H and S in B of H. Okay. So suppose T is they are Hilbert-Smith operator. Okay. Then we want to prove that trace of ST equal to trace of TS. And it's enough to prove you can take S star instead of S. I want to use the polarization identity. So we have S star T equal to 1 by 4 summation. I mean, we have already proved trace of TT star equal to trace of T star T for any T, even when the trace is infinite. Okay, so we can use that here. So trace of S star T, S star T equal to summation I power k into S plus I power k T star into S plus I power k T. Okay. So I can insert the trace here, S star T equal to that, which is equal to 1 by 4 summation I power k. So I mean, I change this expression. I take the so I can write this as S star plus no. So I can use my trace identity. This is equal to trace of whatever is in the left hand side here, but then I can use trace TT star equal to trace T star T. I don't know. I got some warning. So screen is visible now.
Yeah.
Yeah. Okay. So this is equal to trace of 1 by 4. This is equal to 1 by 4 summation I power k. Then trace of something I have, something star something, which I can write it as something star. So S plus I power k T star T, S plus I power k T star. So there is no star there, which I can write star. Now that is equal to 1 by 4 summation I power k trace of this. I can write it as, you can put the one star inside and one star outside. So which is just S star plus I power minus k T star whole star. Okay. And then So this is just S star plus I power minus k T star. Okay. Now I power minus k, I can, which is 1 by I power k, which I can take it to the S star side. 1 by 4 summation I power k trace of T star plus I power k S star whole star, okay, plus times T star plus I power k S star. But then there is an I power minus k, I mean I power 1 by I power k star will be there. But then there is I power k here. I power k star is, I mean I power k star is the bar of that. So that will vanish. That will just cancel. I mean I have 1 by I power k here, but there's a star here. So that will become I power minus k in the denominator. And I get another I power k here, they will get cancelled. I don't know how to write it. Okay? So it's they will vanish. I mean they will become 1. Not vanish. Vanish means become 0. So they will become 1. So I have this. Now this is equal to trace of. So this is equal to, I mean, if you use the same polarization identity, this is same as T. This is what? S plus T start. S star T equal to, it's like this. Okay. So T star, this is equal to TS. TS. Is that right? Yeah. I mean, T star star is here. So you are giving T star there. So this is okay. This is exactly equal to T star, TS star. And you apply the polarization identity for, I mean, this is equal to T star star S star. So which is equal to trace of. Okay. So I have proved it for Hilbert-Smith operators. Right? If T and S are Hilbert-Smith operators, then S plus I power k. This is also Hilbert-Smith. That's also this trace all in all these places makes sense. T star T makes sense. This is for, I mean, I have used the fact that S and T are Hilbert-Smith operators. I mean, I have used the fact that trace of T star equal to trace of T star T. And trace of T star T is finite is what is Hilbert-Smith operator. So that I have used. So for any two Hilbert-Smith operator, I have proved this. Trace of S star T is same as trace of T star, which is same as saying trace of ST equal to trace of TS. Okay. Okay. Now I want to prove for this is okay. If it's not okay, tell me. Now for S in B of H and T in B1H. Okay. And T in B1H is just a span of some positive operators where each positive operator has trace finite. So we can assume that, I mean, the trace is linear. So whatever we want to prove, it's without loss of generality, we can assume that T is greater than 0. Okay? Without loss of generality. Okay? So now we consider this trace of ST. Trace is positive. So trace of ST power half, T power half. Okay, so now T is in B1H. Implies T power half is in B2H. This star is just T. Okay? So because of the T power half is B, and then ST power half is also in B2H. Okay? This is in B2H. This is also in B2H. We have already proved for B2H. So we can bring this T power half this side. T power half, ST power half. And again, ST power half, T power, they are also in B of H. So you can bring this, I mean, you can apply for this up, these two operators. So you can bring this T power half here. So that becomes T, this becomes S. So we have proved trace of ST equal to trace of S. So any doubt? So this is what is called tracial property. Okay? The most important property of trace. What is called tracial property. That's why it's called trace. Satisfies.
So using trace class, there's a problem in the Ghana one in saying that there is no operators x, y, side that x, y minus y x equal to I.
There is a Ghana 1.
And I want to understand there's a problem, right? There is no operators x, y such that x, y minus y x equal to identity.
Yeah. So
Can they be solved using trace? Because the trace of x, y minus y x will be,
I don't think so. Trace, where is trace coming here?
because in the what in the finite dimension case, you take a trace of both sides. Trace of right side is equal to n, or trace of left side is equal to 0.
No, but why should it be trace is defined on those operators? I don't understand what you are saying.
I mean, either you will do something analogous that you do for the finite dimension.
That the operator is there does not exist something like a determinant thing equal to 1. I mean, you have some xy minus yx equal to 1. That's an operator does not exist. That's what you are saying. No?
Yeah. So what you do for the finite dimension case is take a trace on both sides. Trace of right side would be left side would be 0, and trace of left side would be n. But
Correct.
is able to do something similar for the infinite dimension case?
But trace is not okay. You are, but if it's trace is not defined, what will you do? X and y. There's trace.
So, that's the problem. So can somehow compactify the situation to
I
get?
don't see anything because trace is different only for trace plus operators or positive operators.
Yeah.
Trace is
Yeah,
defined.
that's why I did is not a trace plus
Operator,
operator.
positive operator plus a trace plus operator. Any operator you can write it. You can assume that alpha plus alpha. So you can assume that, but without that you cannot do. So yeah, if you can apply trace on that. That's true. But trace of identity is also infinity. There also it does not work in infinite dimension. Trace of identity is infinity, no?
Yeah,
So in any way,
that's the problem.
trace of identity is infinity. So it will not work. So anyway, so this is the trace property, and this is what I want to say about trace. Then I think the duality thing is done reasonably well. So you can look at Vitabda's talk. So I don't really have to say anything. There is a singular decomposition, which I leave it as an exercise again, which is easy, okay, which you can try, and then it's part of the exam. If you have a doubt, we can discuss, but it's easy. So it's better I ask you to do. I should have given it as an assignment, but still, last minute I don't know what to do. Okay? So you anyway submit assignment the Saturday after the exam, okay? Whenever we have the exam. So I will stop. We will discuss something. You want to discuss now, or you want to discuss Saturday?
Saturday will be better. So you can look at this talk.
So you have said Saturday. So Saturday 5:15. Okay.
Then we will stop the recording.
Yeah, I'll stop there.